Another useful tool for probability is Venn diagrams and sets and things like that. So a little bit of terminology to do with sets. So a set is simply a collection of objects. Okay? Those objects we call elements. So some set language. So we can have listing sets. So that's where, well, as the name suggests, all the elements in the set are listed. Example I've got there is the set A, which contains the numbers 1, 3 and 5. I could also describe the same set as a describing set. So instead of writing the numbers, I just describe what the numbers are. And so my set A is the first 3 odd numbers. Now, equal sets are sets that contain exactly the same elements. So if B is the set 5, 3, 1, well, A and B are equal sets. They've got the same elements. An empty set is always interesting. An empty set is a set which has nothing in it. Sometimes you see that called the null set. Universal set, on the other hand, is the set that contains every possible element. So that's sort of like our sample space in probability. A subset, well, that's a set that's contained within another set. So again, if we were to relate that back to probability, that would be like our event space. That would be contained within the sample space. So set C in this example is simply the number 5. It would be a subset of A. It would also be a subset of B. Intersection, well, they're the ones that they have in common. So set D is 2, 3, 4. The intersection of A and D is simply 3. That's the number that they have in common. Union are the elements of both sets joined together. So the union of A and D would become 1, 2, 3, 4 and 5. Complement, just like in probability, are the objects that are not in the set. So it's the logical opposite, if you like. So a universal set is the first 6 integers. So say we're just thinking of the first 6 integers, then the complement of A would be 2, 4 and 6. Because 1, 3 and 5 are in our set. Therefore, 2, 4 and 6 are not. Some set notation. Okay, the null or the empty set, 2 ways of doing it. I could just have the braces to indicate it's a set with nothing in it. But the 0 with a slash through it is another symbol for null. Some of you might have seen that if you're into computing. That's the symbol they often use for null. The funny E, I suppose you could call it, that stands for is an element of. So the number 3 was an element of A. It belonged in set A. The absolute value sign, or what we're used to seeing as the absolute value sign, or another way of writing it would be N with parentheses, are the number of elements in the set. So I could say, well, the absolute value of A is 3 because there were 3 members in that set. The sideways U, so U sort of fallen over, is a subset of. So that's the symbol for is a subset of. So C was a subset of A. C was also a subset of B. B was a subset of A, but remember they were also equal sets. So you'll notice the subset symbol, but with a line underneath it. It's both equal to and a subset of. And the null is a subset of A because the null set is a subset of every set. It's weird, I know, but any set contains nothing. It contains other things as well, but it also contains nothing. So the null set is a subset of every set. Intersection, so that's our upside down U, and union, U for union. Complements, probably the most common is the bar on the top, much like we see in probability, but other ways you might see it is the A with a dash, and not to be confused with the derivative, but that's later. An A with a C for complement, but as I say, the most common way of doing it would be A with a bar on top. All right, Venn diagrams then, because they can be useful. So this is a visual way of looking at the situation. So usually the universal set, or sample space if we're talking about probability, is represented by a rectangle. And then all the other sets are within that rectangle. So there is an example of all those ones I just talked about. So the universal set, remember I said, contained all the numbers 1, 2, 3, 4, 5, 6. The set A and the set B were equivalent sets or equal sets, and they both contained 1, 3 and 5. You'll see 1, 3 and 5 is inside both B, but it's also inside A. The intersection of B and D, we said, was the number 3. The complement of the set A was 2, 4, 6. So 2, 4, 6 are sitting outside of the set A, but 2 and 4 were inside the set D, so there it is there. And the set C was simply the number 5. So that's how we could visually represent all that information. So here we go. C is a subset of B, so there it is inside B. The intersection of A and D, so that's what A and D have in common, or where they overlap. Union is everything in both, and it's so good I did it again. I have no idea why that's there twice. Okay. Disjoint sets. Now that is equivalent to what we said in probability of mutually exclusive. So disjoint sets are ones that have no point of intersection. So you might say C and D in our example are disjoint sets because they had nothing in common. So Venn diagrams and counting. So how do we use them to solve our probability problems? So it's another way, I guess, of listing all the possibilities. Okay, the counting rule for sets. The number of elements in A union B will be the same as the number of elements in A plus the number of elements in B, but we would take away the number in the intersection because we don't want to double count them. So Sam's class at school. And oh, how appropriate, we just had a swimming carnival. Many of the students are on the swim team. There are only 18 students in this class. 7 swim freestyle, 4 swim backstroke, and 2 swim both. Find the probability that a random student is not on the swim team. All right, so the universal set, there's my rectangle, that's the whole class. I've drawn 2 sets inside there for freestyle and B, was backstroke, was it? Yes, backstroke. And they do overlap because they told us some swim both. So where do we place everyone to work out this question? So I go through it. Well, the first number I'm going to place is there. I know there's 2 students in the intersection. So they swim both. Now, they also told me 7 swim freestyle. So there must be another 5 in the freestyle set. And we've been told 4 swim backstroke. So there must be another 2 in the backstroke set. So that adds up to, what's that? That's 9. But there are 18 students in the class all up. So there must be another 9. So I worked out 9 by looking at the sets and doing it logically. Or of course you could use the formula that we just saw there, the counting rule. It will work out how much is in the union. So therefore, there must be 9 not in those 2 sets. So I'll just put them outside the 2 sets. We can now answer our question. Probability that a random student selected is not on the swimming team. Oh, well, it's 9 in 18. There's a 50-50 chance for that one. So C and D are to do with Venn diagrams.